Welcome to the one of the biggest things at this conference, the discussion panel. I hope that you get a good lunch, you got a lot of energy, because we got interesting topic to tackle today. And as we will be discussing, not only functional programming, but also the real world at the same time. So I have a pleasure to moderate this discussion. And as always, let's start with introductions of our panelists. And maybe we can start from the left. 1 second, I will give you a mic. Stage left or So yeah, please introduce yourselves.
I'm Evan Czaplicki. I created the Elm programming language.
My name is Howie. I've been doing open source Scala for about 12 years and do developer tools professionally.
I'm Martin Odersky, you know me.
I'm Dimi Racordon. I work with Martin and I'm the creator of the Hydro programming language.
I'm Ralf Jung. I'm a professor at ETH Zurich and I work on Rust.
And I'm Krzysztof from Virtus Lab, and you know what I will do today. And I don't know, I'm lazy, so is there any questions from here? So we can kick it off.
We should have opening statements.
Opening statements. Okay, sorry. Let's do opening statement first.
So you start from there since you said
Okay, sure, right. We were asked to come up with, what did you say, controversial opening statements. So my opening claim is that Rust is a functional language. And so to seems that sufficiently controversial. Nice. So to justify that, I mean, first of all, it has many of the hallmark features of functional languages. It has algebraic data types, full support for pattern matching. Everything is an expression, and that's like the idiomatic Rust style. Everything is immutable by default. It supports first-class functions, and that's also considered idiomatic. And of course, it does support highly imperative coding patterns, but then there's mutable state in OCaml and in Scala, and it's still a functional language. So, and furthermore, there's a less obvious reason for that, which is if you look at the core fragment of Rust, like no unsafe anywhere in the program, it turns out that's actually that's a language which you can, in a structural, like compositional way, directly translate to a purely functional language. Because due to these aliasing restrictions, a shared reference is just a more efficient representation of just making a copy of the value it points to. So you might as well say &t is t if you don't care about performance. And a mutable reference is an interesting way of kind of encoding a function which takes the value and then returns a different, like a mutated form of the value, except with the additional guarantee that it's an in-place update. So if you don't care about performance, you could just imagine making copies of mutable references. And this, like, superficial at first analogy can actually be pushed all the way through for arbitrary use cases of mutable references. And this is in fact done. There's a tool called Aeneas that does that can translate Rust code to Lean or other verifiers to then do functional correctness verification. So in that sense, there's actually also a deep theoretical foundation to this claim that core Rust is a functional language.
All right, so Ralf stole my thunder because I wanted to make the exact same argument for Swift. I'm here for representing Swift. So I guess it's not very controversial to me. So I'll try to push some in another direction. So on Tuesday, Martin said that Scala was a functional first language that was on design, and I really appreciated that thought. But one thing that I would like to push against is that generally there is this unchallenged idea that functional programming is just better, intrinsically better, and that you might concede in some places to not do functional programming because, well, you need to make it efficient. And I would say that actually it should be the reverse. We are living in the real world that is imperative. Things move linearly. Things change. The world is a stateful world. And so the way we think about the world is an imperative way to think about the world. And so to me, the natural way to express things should be imperative, and we should use functional programming as a concession to create abstractions and capture things into pockets that make sense in an overall world that is imperative.
Wow. Okay. So my statement is that functional programming was an academic dream that made it to industry, and there was, to some degree, a rude awakening. In the academic dream, everything was simple and beautiful and well composed. In the industrial world that we see functional projects today, often they are just as gnarly balls of muds as their object-oriented predecessors. And I think we as a community need to get a certain humility that these things can happen, and that functional programming is not a surefire recipe for doing everything better. So it's in that degree, to that degree, I agree with you. But it's not all doom and gloom like my conferences to the left. So I believe functional programming does have a very bright future in the quest to make programming essentially understandable, reliable, and safe. And that's in particular important in a world with LLMs, because we will have more and more auto-generated code and untrusted code, where you say, well, if something like a resource gets cheaper, like raw lines of code, then you can raise the standards. You can really say, I expect more of my programs than just to spit out something and say, well, here's something which might work or might not work. Dear reviewer, please give your okay for that. So I think we will have the resources and the need, because things will be untrusted, to raise the standard of essentially what we expect from our programs. And there, I believe functional programming does have a bright future, in particular strongly typed functional programming, because types and functional programs are right now the best way we get to something that is essentially a specification we can trust. The problem with essentially proofs is always, what is your specification? And I think, like Ralf said, if your specification in your keynote in the morning, if the specification is not checkable, then it will have bugs and it's worth nothing. So you need executable specifications, and functional programs are the closest things we have to that right now.
Okay, so the most controversial statement. I think that the programming language ecosystem is generally efficient, and the reason why things that we like don't make it big or become mainstream is that they're just not good enough. And that includes things like Scala, that includes things like Akka, Cat, Zio, Scala Z, all the commonly Howie stuff, Ammonite. It's good in some ways, and that's why we all like it, but we also have to acknowledge all the ways that they are not good and be realistic about it and try to improve it. So like when I started using Scala in 2012, it was a complete disaster trying to use it as a student. And just trying to set up like a photo sharing website for a side project was completely crazy. So things have gotten better and things will continue to get better. But the silver lining of this is that if we acknowledge that things aren't great, there's so many ways that we can make things better. And if you make things better, things can change. For example, Python was a nothing language until 2010, about 15 years in. Java was kind of the slow, stagnant language for 20 years until recently it's becoming hype again. So I think that Scala has a lot of room to improve. I think that if we acknowledge all the weaknesses, all the poor documentation, bad error message, overcomplicated APIs, kind of fragmented ecosystem, and we make progress towards improving those, there's a lot that we can improve in the Scala language more than just complaining on Twitter or Reddit.
So the best I can do is that the main thing we should learn from other languages is we should actually look at PHP and take the lessons from them. Okay, so let me explain. I try to be a language enjoyer and try to see what's good about all different languages. And one thing that I think in functional languages we often don't emphasize enough is immediacy of being able to have someone say, I want to make something, and then within 5 minutes or 10 minutes, like they made it. Whether or not that's good, that's a separate dimension. Like whether the code is good is a separate dimension, but that immediacy I think is really important. And I think we could see a lot of more people getting into functional programming if they had that immediate experience of, I want to make this server, I want to make this chart, and then they can make it. So.
Thank you so much. And now it's not only my laziness, but you need to save the room because the questions I'm going to ask is like each PHP functional. So let's open the room to the questions to our panelists today. Please raise your hand. There is the first one.
What's the name of the tool that compiles Rust to Lean?
Yeah.
Oh, yeah. Sorry, what's the name of the tool that compiles Rust to Lean?
It's called Aeneas, A-E-N-E-A-S, I think. Microsoft Research and Jonathan Protsenko and Sean Ho.
Okay. I'm waiting for the next one. Remember, PHP is still waiting for us. There is a question.
I have a question for Martin. So he says that in the LLM era, type systems can really be more useful because then for the code generated by those LLMs, type systems are providing us with the safeguards that can actually prevent a lot of nonsensical code. I want to ask, what do you envision the future of type systems and what they will look like, given that, because in the future, maybe we can actually use more precise and specific type system, even closer to program logic that precisely describes things, and we even ask LLMs to prove them themselves. And I think that's interesting me a lot, and I want to know what you think of it.
I think it is a super interesting topic for development and research to do that, to have more finer-grained types. The danger with fine-grained types is always that essentially when you get errors, then they tend to be really hard to essentially address because we don't have the tools like debuggers for them right now. So that's another thing to work on, to say if we have super detailed type specifications, and I agree that they can possibly help, and maybe that's the future, then we need somehow ways to save people who are fighting with that, because right now the story is not pretty. Right now I think the story is a lot of people are giving up on a technology, on a language, because they find it's better to just debug low-level C code than to debug an inscrutable type error message, and we have to change that.
So something that I've seen happening a bit in the TypeScript community recently is there's been a bit of a pushback against these what's called hypertyping, where like you have APIs that are so well typed, you might say, that like a normal developers can't look at these types and these functions and understand how do I use this. They just have to be taught how you use it by the guide. They can't look at the function type and to understand how you use it. How do you think you can avoid situations like that in other languages?
I think one way to look at this is the type system is a summary of the or approximation of the behavior of your program. So the reason it's valuable is that type checking usually is faster than running all your integration tests, and the types are usually simpler than all the implementation code. But if your types can get simpler and more complex, as your types get more and more complex, your type checking does become slower than running all your integration tests, and your type signatures do become just as complex as your implementation code. So there's no real hard boundary between the two, and you just have to make a judgment and say, like, I think this is the valuable things that people have to care about, and the type checker is a check. But it cannot check everything, and if I try to check everything, the type system just loses all value. It just literally becomes the implementation code that's underneath of the types. So I think you just have to make an arbitrary decision and say this is what the type system has to say.
One thing I'd like to add to this, and that also relates to what's been said before with the LLMs, is I think types are useful for humans. Because there are this summary representation of things, and we humans tend to use types correctly because we get the sense of why we should use types, and we try to make the type fit the data that we want. But if we just rely on types to be a sort of OK check because the type checker said yes, then there are obviously ways to just type everything with any, and then sure, it's well typed, but it serves no purpose. So I really think that if we want to rely on types as a way to have the guarantee that all code is correct, we have to have humans here keep making sense of the types and using them properly. If the goal is to ensure that generated code, for instance, is correct, then I suppose types should be just removed, because then we would get to just values. And what's the point of having a type system that just reproduce what the value, the runtime of the program is already doing?
Okay, thank you. There is a question.
Hello, thank you. So that's additional question on top of the previous speaker. In industry, I experience from time to time that people, while languages and type systems even become more complex and complicated and harder to grasp, people kind of tend to downshift to the languages which don't really have these sophisticated type systems, like this Rust versus Zig, for example, where Rust have more or less sophisticated type system, whereas Zig has arenas and all the tooling kind of to test your code and prevent memory leaks, but like after testing, so after runtime check essentially. So what do you think about this like downshifting and informational overload which being imposed on developers while type systems becomes more and more complicated?
I'm not super, I mean, I know the broad scopes of Zig. I have not used it myself. I think it's a super interesting language. I think it will be curious to see where it goes. Currently, it doesn't really have much of a memory safety story, but it certainly improves a lot over C. I mean, maybe that's my biased impression. I don't see a lot of a shift from Rust to Zig, but also Zig is still very young, so I think it's too early to evaluate that. I think there's certainly domains where Zig works better. One of the interesting examples that I heard about recently where they used Zig over Rust, however, was actually a case where Zig does more typing than Rust, because they wanted to control, or like typing maybe, but like in quotes, because they wanted to control more tightly where their program does allocations and doesn't do allocations. And Zig is super tight about that. You can't just allocate anywhere in your code. You have to actually pass through the allocator, whereas Rust lets you allocate everywhere. And so in that case, they use Zig because there it tracks things more precisely than what Rust does. And that was what they needed for this use case. So if anything, that was more of an upshifting in control and not a downshifting. So I mean, certainly you can overdo it, and you might get like a type system winter if you tell people that they have to like type everything all the time with super detailed. But so far, at least in Rust, it seems to be working out. I mean, Rust is still growing, and people are adopting it despite the difficulty of having to put all those types there compared to C, because they get a clear value out of that.
Yeah, so my experience with getting into very complicated type systems was, as an undergraduate, I took a course where we were working with theorem provers, and we were writing dependently typed programs where, okay, we can write a compiler where we take our AST and we have proved that the optimizing version produces the same results as the naive version. And this was one of the classes where I was just like, this is too hard. I can't do it. I don't know how to do this. This is crazy. You know, they were like, okay, you did nice on that one, but now we are going to add a mutable variable. And I was just like, I can't pass this course. So those kinds of features do exist in Haskell, like languages that I use, but I very rarely touch. So I think my view is kind of like, these features are very exciting and they're very powerful. And I think culturally, we let that excitement override a pure pragmatic evaluation of what we should do in practice. So like, there are many cases in my compiler where I could be more precise, but I shouldn't. And so for my own code, I really ask about each thing is like, how can this be the simplest version that it can be and be the level of quality that I want? And I think that's where it is a cultural issue. And I mean, in Elm, I take an approach of like, we'll solve the cultural issue by just not having the features. But that's partly because in functional programming, there is such a strong culture around, what if I could use this interesting feature? And so I think part of the draw for some users is that it's very exciting. And so yeah, that's my feeling.
Kind of in that vein, like I talked to someone who used to be doing Scala and ended up doing Python after a few years, and they told me one of their revelations was, you don't need all these things to write software. There are many ways to write software. Some are harder, some are easier. No single programming language or no single approach has like a monopoly on the correct way to write software. And one of the particular things they brought up was, they were wondering, why did they always write things in finally tagless before? Like, you can use finally tagless. It's an extremely powerful tool. You can do a lot of things with it, but you can also not use it in many cases, and you really need to make a considered judgment. Is this the right tool for the job? Am I just using it because it's exciting, like Evan said, or am I using it because it gives me some particular properties that other approaches do not give you? I think many of the Scala ecosystems in the past have gone too far and just used the same hammer everywhere, whether that hammer is async or IO or some other things. And we really need to be more like measured. Like, do you really need a monad, or could you use an applicative, or even just a normal functor? And have you really thought about all the different options before just randomly choosing some abstraction to use?
Just to add on to that, that's like in my own compiler, every time I'm writing some instances, I always say, what is the minimal? Like, can it just be a functor? Can it just be applicative? Can it just be a semigroup? And none of those other things. So, and I think that really, really helps keep the code simpler. And it's like, yeah, culturally, not all people excited about the languages take that approach.
I fully agree with that. The issue is, once you are part of a larger team where standards have to be set, or once you have a whole language ecosystems where essentially libraries propagate or not, and certain libraries become popular. So sometimes I quip that it's the job of language designers to protect language users from libraries. And but I find that very difficult. So I think there has to be a certain spirit, and maybe even a realization of what is complex or not, because it's definitely not the case that, I heard that sometimes to say, well, if it's done at compile time, it's free, right? So any sort of runtime bug that I can eliminate at compile time is basically 100% win. And I would completely disagree with that. Compile time has a cost, and the cost is real, and often it's worth it, but sometimes it's not worth it. And as everything, if you push everything to 100%, then you are no longer on the optimum.
Yeah, and just to add on to that, like in Elm, we've considered fancier features from time to time, and this is exactly the fear of, like, if this gets added, that's going to go into the libraries, then it's going to go through the whole language. And so in a way, like, one approach that I like thinking about from the Elm perspective is that if the simple system works, you can stay there, and then once you hit a hard boundary where you need fancier types, or you need something that can get you more mutation and performance, then you pop out to a language where you're there specifically because you want the things that are there. But that means that for the simple things, you don't get the fancy things going on there where they don't need to be. But.
I fully agree. I would also add that I think it should be our work as language designers sometimes to say no to features. It's hard because users really want something. And I think as users, it should also be our work to sometimes stop and think, do we really need to program things that way exactly? Right? If you find yourself in a language that has some constraints, I think sometimes it's easy to think, oh, but then the language should do this and that and that, and so obviously I can do the pattern that I've been using for 20 years in this other language. But maybe this pattern is wrong, or maybe this is not the right fit for the language that you are using. And so I think sometimes users, we should stop a little and just think, is it okay to concede to try another approach? And maybe if that approach looks weird, a bit alien, maybe there is something to gain from it, just by the fact that not adding this other complexity that would allow me to do things I've already done. I've already always done the same way.
Yes, it's interesting to hear some of these comments because it seems we are grappling with some of the same questions in Scala that we are grappling with in Rust with respect to making the type system more expressive and what impact that has on the ecosystem. So we have similar discussions there. Like people are like concerned that the libraries get too complicated and nobody can read the documentation anymore and things like that. So definitely a real concern. I don't think there's a simple answer to that. One of the things that helps, I think, is like if you have a healthy large enough ecosystem, you will have people trying to implement the same kind of functionality with different approaches, and then you can, like, people can choose, and you see which approach works better for people, and then maybe it turns out the super strictly typed version is just hardly used because it's way more complicated, and everybody switches to the other one. Like you kind of some amount of just playing it out in practice and see what actually works for people for real in when applying this in industry. And maybe both can coexist because there's reasonable applications for both of them. So yeah, there's some amount of protecting the language users, but there's also some amount of like providing sufficient playground and ways for people to then experiment because you don't know in advance what will actually work in practice, and there's probably different situations where different things work.
So from what you have been actually speaking, there are two things here. One is the thing that people go, for example, to implement tackless final everywhere because they find intellectual satisfaction, or people prefer to learn languages where you can just write something in 5 minutes and get it to work, which is instant gratification. So both of these things are like the reasons for people to do things. But then I think we are missing one thing that put us in the situation. So I would like to know, what is your point of view of the problem of force of habit? When something that is wrong just stays there because of habit. So what is your point of view on that?
So yeah, I think this is an actual plague on software development and on language evolution. I think force of habit is extremely powerful, and people often get convinced that there is no other possible way to do a particular thing. And I suppose that's, for me, one of the reasons why it's interesting to have people keep wasting their career developing new languages, is that it gives playground to experiment and like face the constraints of a language that is young enough to not have to contend with a community that says we absolutely need this because it's our core business. If you have 10 users, like Hilo has, then you can say no to anything you want, and you just be friend with the 10 users, and you can tell them, no, sure, really try. I think having those languages is a way to try to avoid this force of habit.
I think one way to look at it is what makes people like have free will and intelligence is that they can choose what to do. Like the difference between a person and like water is that water always just flows downhill the same way, completely predictably. And in some ways, people can do the same thing. Like people will default to the easiest path to do things the way it's always been done. But people don't need to do that. And kind of measuring how intelligent the individual or community is as a whole is, can they resist the urge to just do the same thing they've always done? And can they plan for a better thing that may have some upfront cost? And habit is real. Like it takes a lot of effort to stop water flowing downhill. But there are things you can do if you plan around it, if you really do research, if you really sell the value proposition of what could be in the future. Like that's what leadership is, right? Leadership isn't just following where everyone goes, that's being a follower. Leadership is saying, you want to go that way, but I can promise you there's a better way this way, even though there's some pain up front. If we beat through the pain, we can get to a better place in the future, selling the dream. So it's not easy, and there's millions of talks and books about how leadership and innovation works, but it's fundamentally you have to do it in order to get away from the current situation that may not be what you want to be.
On the topic of the easy path for programmers, so in Elm in particular, I took that into account, especially in the foreign function interface. How does it interop with JavaScript? And for me, a big concern was if I am too lenient with the interface, someone's going to say, okay, I just want to write jQuery. I just want React and Elm. And so Elm would be swamped by people who already are familiar, potentially like experts with these technologies, and they just want that same thing, but with the type system. And so my approach in Elm, because it was in that context, was to say, okay, we have a quite strict way of interoperating with JavaScript that lets us keep our things that are valuable to us. And now with my work on database, with databases, the culture there isn't the same. It's like if someone's coming to use a language that compiles to a database, they're not going to say, well, I want to use all my same libraries that I already use. It's like, what are the Postgres libraries? Like the culture is very different there. And so I at least have been very influenced, like the designs I make are often based on how it will be received, what is the culture, what are the specifics of that, of that group.
There is a question.
I'd like to bring together two topics that you've mentioned. One is the increasing complexity of the type systems and notational overhead and understanding of signatures and stuff. And the other is error messages and being friendly to display error messages that make sense to the users. What do you think about the relationship between the fact that as type systems become more complicated, you also want to infer as much as you can so that the people don't have to write these types, but then the error messages that you get actually tell you about things that you never wrote in the first place because they got inferred in the process, and then the inferred things did not match.
So I can say in the context of Elm, a lot of so getting the error messages nice is essentially an engineering effort that takes a decent amount of time and thought. And it's not necessarily like a super publishable or like super interesting in an academic way pursuit. And so a lot of what went into Elm is like when I generate my constraints, I do it in a very specific order so that even if something is implicit, it's done in a predictable way. So I say, okay, I know this, and the programmer, as they learn the system, will become familiar with how it works. And so I think for more complicated type systems, using that approach, it can go quite far. Like when I think about what are the possibilities in Haskell, like I think the kinds of things that I tried in Elm could work for type classes, and I can't say how far it goes. But I do think primarily it's an engineering effort that the core barrier is like having an organizational model and a funding model that will permit that work to happen without like someone losing their job or something like that.
Yeah, I mean, I think what I can contribute from the Rust side there is like setting a community norm and expectation that the compiler treats you decently in its error messages makes a big difference. Rust didn't always, like Rust 1.0 error messages were a lot worse than they are today, but at some point, a small group of people got together and made it their mission to make the messages amazing. And since then, that's kind of what people expect. And so we have like official, you can report a bug, and like this diagnostic is not as good as it could be is a category of bug that we officially accept as a bug we will track, and there is a team responsible, a working group responsible for improving the quality of diagnostics. And often those kind of issues aren't even that hard to implement, so it's also a great way to, like, Rust is a very open source project with contributors just doing things for fun in their free time. There's not one company backing it. And diagnostic improvements are usually a fairly easy way for people to get into development, because you don't need to understand most of the compiler to figure out how to give a nicer error message for this case, and it's very clear how you write a test case for that and things like that. So like once you set these kind of norms in the community, this also becomes a self-reinforcing and self-improving kind of virtuous cycle.
So I disagree a bit in the sense that like if the goal is to simply like modify the text that's given in a particular case, perhaps that's easy. But so like in the context of Elm, like when we went from having the kind of error messages you would expect from type-inferred languages to having them nice. It wasn't actually a goal of mine. My actual goal was I wanted to output the error messages as JSON. And as I was doing that and going through, I noticed, oh, I can actually restructure this such that I can get additional information, and that additional information can help me produce better error messages. So it actually was a re-architecting and like a quite deep change that crossed a lot of the compiler to be able to get the rich information that I needed to be able to write high-quality error messages. And so once you have that information, yeah, you could tweak the text here and there, but I think like for a language like Haskell or something like that, it is crossing the whole compiler to get the information you need at the time when you're actually giving the errors.
Yeah, we also have an ongoing effort, but I think we still have a lot of work to do to get better error messages. But I think I agree, it's not an easy thing at all. So the danger is that you see an error message and say, hey, I can improve it, and then you propose to do this and this and this, give lots of explanations, and then it turns out that actually this case was maybe 5% that this thing was triggered, and now you get lots of information which is not relevant for the other 95%. And that you need to see, even for simple error messages, you typically need to see the whole thing. Like, where else is this thing raised? What are common errors? What are less common errors? In particular with hints how to fix things. If you just have your special thing and you say, well, do it like this, and in 95% of the cases it's wrong, then it's worse than not having anything, right? So that, I think it requires a lot of taste and a lot of expertise, but it needs to be done. It's absolutely essential. And I mean, if we can put together a working group like that in Scala of experts that do this, I would be delighted.
Yeah, I mean, I didn't mean to say that it's simple, in particular not the initial bring up. Like, certainly the initial work, there was a lot of re-engineering and re-architecting, but there's also, like, once you have that, it's more than just textual changes, which become a lot simpler. Like, once you have the infrastructure that allows you to make the right kind of queries to figure out what are the other candidates that I have here, like what are other things that the trades could resolve, doing this in a way that's isolated so it doesn't influence the rest of your type checking, like diagnostics only queries and things like that. Once you have that, adding more cases, not just text changes, but like recognizing more patterns that are reasonably common and adding nice error messages for them is, I mean, it's not trivial, but it's doable also by people that don't have experience with the entire rest of the code base.
To the point of inference, one thing I'd like to mention is that I often have issues with people like developing very complicated systems or libraries, right? It's not just language, it can be library design too. And then just claiming that it's all fine because inference just works, right? And it's very easy, for instance, to show a super nice C++ template library that does amazing thing. You have the best DSL ever. But once there is a mistake, then you're just completely lost. And so I think the complexity of a system should not be measured only by how nice you can build examples, but when you present something to users, they should understand it all, including the things that are not shown. It's nice to align annotations, but type parameters are still there, right? Whether I write it or not. So I think as language designers or library designers, we should use inference with care.
And this is also something where the language designer can help the library author. Like in Rust, we have attributes that you can put on your traits to steer which diagnostics are emitted for error messages. And that helps a lot because instead of just seeing some random, like this trait isn't implemented, you get some much more on-point information. The compiler does emit suggestions for what you might want to do, but like its general heuristics don't always work, so you can use attributes to steer that and things like that. So there's things there that the language designer can give tool to the library author to then, for both of them together, to help the programmer that uses that at the end. So if you get a healthy kind of exchange between language designers and library authors, there's a lot you can achieve there in the end overall for the ecosystem.
Okay, I think we are just at the time. So let me first thank our panelists for wonderful discussions, for the insights and ideas going ahead. Thank you everybody here. Thank you for people that asked the questions.